Hello there, cutie patootie math angel. Welcome back, and a very warm welcome if you are new around here. This is Decaf-Math ASMR. Thank you for choosing to join me today. So today let's chat about the addition rule for probability. The addition rule. And I hope that you'll forgive me because I think this is our very first video on probability here on the channel, but we're not starting from the absolute basics. But I think this is usually introduced very early on in a probability class anyway, so don't think it's too big of a deal. But this was requested, so why not just jump into it? And I think we'll end up mentioning some very basic ideas throughout this anyway, so I think we will be okay. If you are learning this, I do hope that something that I say is helpful, or maybe this makes for some nice review. For everyone else, I hope that this is relaxing and soothing, and maybe a nice little distraction from whatever you're up to, in a good way, hopefully a nice diversion. Or maybe this is boring, just boring enough to help you get to sleep, whatever the case may be. I hope this blesses you in some way. There's absolutely no pressure here, okay? So don't worry about whether you think you're good at math, bad at math. If you think you're the absolute worst at math, believe me, you're not. But or somewhere in between, or if you like math or hate math or are unsure about it, it's all okay here, okay? I like to remind you of that. It's all okay here. It's all okay. So, this is just math ASMR school, so feel free to just zone in and out as you like, okay? Alright, so let's start out with the formula. So that's the game plan. I'm gonna write out the formula. We'll take a look at it and break it down a little bit. And then what we're gonna do is work out a very simple example that has to do with a standard deck of cards. So 52 cards. And I think that might come in handy. I think when we learn or review formulas, that it can sometimes be helpful to keep an example in the back of our minds to remind us what we're kind of after, the key concept and the key parts of our formula. So I hope that comes in handy as well. And so let's start with the formula itself though. So I'm gonna write it out and then we'll break it down, okay? There we go. So the addition rule for probability, right? So let's read it out loud first and we'll break it down. So the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersect B, or the intersection of A and B. Okay, so what are all of these things? So A and B are what we call events. And so if you've heard the word probability before, it's okay if you've never have, but you might associate it with the idea of likelihood or chances of something happening. So when we talk about probability, it's a number that we assign to uncertainty to represent what we think is the likelihood of something that is uncertain. So when we think of events, basically we want to keep in mind this idea of a sample space, which is basically all the possible outcomes of whatever it is that we're modeling, right? So all possible outcomes. outcomes. And then out of all of those possible outcomes, how many ways can we have an actual situation happen? That's the general idea for an event. So a very simplistic example of that would be flipping a coin, which if you're in a probability class, you've probably dealt with coins, probably dealt with cards, probably dealt with rolling dice. So all of these are very classic examples, but let's say I'm just going to flip a coin, let's say quarter, and so it's going to either land heads or tails, right? We're not going to worry about the landing weirdly on exactly one of the edges, which is kind of bizarre, but just a fair coin, right? Just heads or tails. And so yeah, that's it. So that would be our sample space. The set of all the possible outcomes would just be heads or tails here, right? Just flipping it once. And so an event that we might want to calculate the probability of would be what's the likelihood of the coin landing heads. That's it. So that would be an event, right? It's the thing that we're trying to see, like what is the outcome and like what are the chances of that outcome happening. So usually when we want to find the probability of it, we consider whether that outcome is a success or a failure. Just conceptually, the idea of either it happens or it doesn't happen, right? So we're going to try and model this out. If we do this with the law of large numbers, meaning if we continue to do this, if we flipped the coin over and over and over and over and over again, it either is going to be a head, which is our event, or not, which would be a tail, but or not a head. So that would be a failure. And so if we were to count those all up, that's this idea, right? So that's what our event is all about. So we want to keep in mind what our sample space is. What are all the possible outcomes that we're looking at here? And then what are the events that we're dealing with? Okay, so that's just the general idea. So the probability is a number that we assign to represent the likelihood of an outcome for something that's uncertain, basically. And that number itself, that probability, needs to satisfy certain axioms, but they're actually very intuitive, but still important to think about. So we'll do that in another video probably, but just keep that in mind. Like, it's not just some random number here that we're coming up with. So anyways, we'll get into that later on, but keep that in mind. So in this case, we have the probability of A union B. So now we have two events and we're combining those two situations, okay? So A union B is kind of putting them together, and you might think that's an and, but it's actually or. So the probability of either A happening or B happening is what this union is about. Okay, so it's an or statement. So either A or B is equal to the probability of just event A alone plus the probability of B. So that's the addition rule for probability part. Then we have this minus the probability of the intersection of A and B. So that's where we're talking about the and part. So this is A and B. So that's it. The probability of either A or B happening is the sum of their individual probabilities and then minus the probability of A and B happening. Now this leads to this question here, which is if the two events, well, it's whether the two events are mutually exclusive. In other words, is there such thing as an A and B? So what this means is if there's such thing as satisfying both, if events A and B are mutually exclusive, they are mutually exclusive, then there is never a situation, no outcome that satisfies both event A and event B, or like is in event A and in event B. If they are mutually exclusive, it's one or the other, or in other words, they are disjoint. Okay, so disjoint and mutually exclusive are synonymous for the most part. It depends on what context, but I think the best way to think about it is to picture a Venn diagram. So for mutually exclusive or disjoint, we're talking about this picture here. If I have event A happening and event B happening, you see that these two circles don't overlap or intersect. But if they're like this, where this is A and this is B, then they do intersect here. And you can see that because this whole circle is A, so everything inside of this is A, and this whole circle here is B, so everything inside of this is B. So you could see that this part overlaps both of them. So this is A and B, or A intersect B. Okay, as far as like sets go, or the possible situations that lie in both of them. Okay, so here they are not mutually exclusive because there is stuff that intersects both of them. Here they are mutually exclusive because they are disjoint. They're disjoint, and then there's no stuff that goes in both A and B. So you might hear mutually exclusive and disjoint used interchangeably. Okay, so just for some intuition though here, the idea is that if A and B are disjoint or are mutually exclusive, then there is no such thing as being in both A and B, so the probability would be 0, which means this whole thing goes away because the probability of nothing is still going to be 0, and when you subtract 0, that goes away. So if A and B, whatever you're working with in the context of, the question or the model or whatever you're working with, if they are disjoint or are mutually exclusive, then you can just go ahead and say the probability of either A or B is just the probability of A plus the probability of B. But if they are not mutually exclusive, so let me just make this clear, this mutually exclusive is for this part. If they are not mutually exclusive, then there's this intersection part. And basically, just kind of for some intuition building, the reason why we have to subtract this out is because if we do the probability of A, it's just this whole piece, including that and part, and then plus the probability of B, which would be this whole piece, including that inner part, then you basically double counted the part that overlaps. So you want to go ahead and subtract one of them out. Okay, so that's why we just want to subtract the probability of A and B as well, just to make sure that we're not double counting anything. Okay, so I hope that helps, or is a good little review here. So depending on your question, if you see the probability of this or this happening, then you want to consider if the this or that, if they're mutually exclusive, or if there are situations where something could satisfy both of them. And depending on your answer to that, you would do the probability of this plus the probability of that minus the probability of this and that, or just get rid of it if they are mutually exclusive. Okay, so then let's go ahead and look at the card example, because I think that will help us remember this formula a little bit. And let me show you the setup after I erase this. Okay, so the question is going to be very simplistic. Let's say I have a standard deck of cards, so 52 cards here that it'll be 52 because we're not going to include jokers, okay? So the question is going to be, if I were to draw a single card out of this 52 card deck randomly, okay? So let's say they're all shuffled, and never mind the fact that my fiance and I recently played gin rummy, so this isn't really shuffled, but let's pretend that it is. So I'm randomly selecting one card, okay? So it's important to kind of know the context of whatever question. We're not pulling a card and then pulling another card without replacement, all of that stuff. This is way more simple than that. We're just gonna pull a random card out of a 52 card deck, okay? So what is the probability of either drawing a queen or a heart? Okay, so that's the question. Okay, so you can think on that if you want, but in the meantime, I also wanted to kind of do a quick little run through of a 52 card deck. We can take our time for some nice sleepy ASMR, I think, with this, but I'm not going to assume anything. So with 52 cards, they are divided into 4 different shapes, are called suits, right? So suits or shapes, but they're suits. So the 4 suits are spades, clubs, which kind of look like broccoli or something, clubs, okay, hearts, and wherever a diamond is, diamonds. Okay, so we have 4 suits, and 52 cards divided by 4 gives you 13, which means that there are 13 cards or numbers in each suit. So the numbers go 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we have a jack, which is a J, a queen, which is a Q, and a king, which is a K. And then we have an A, which is the diamond one that we had was an ace of diamonds, which, let's see here we go. This is an ace, an A or an ace, okay? So depending on your game or whatever, ace is sometimes a 1, like ace 2, 3, 4 to 10, and then jack, queen, king. And sometimes ace is higher than a king, so sometimes it's 2 through 10, and then jack, queen, king, ace. Just depends, okay? So that's how we get 13 cards. It's 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, and ace. So that's 13 cards of each suit, okay? And that's all we need to know for this question anyway, but I just didn't want to assume anything. But the probability of a queen or a heart. Alright, so we have an or situation, so let's go ahead and use this formula. So we're going to take the probability of each one individually and add them. It's the addition rule. And now we want to consider if this part exists. Is there a situation where we have both a queen and a heart? I'll let you think about that. And a heart. Is there a situation, that's such an ugly and. Is there a situation where you have a queen and a heart? I'll let you think about that while I dig here for a second. Queen and a heart. Well, that is yes, right? This is the Queen of Hearts. So literally a queen and a heart. I'm not saying that to be sarcastic or condescending or anything. I just think that sometimes it's so obvious that it's easy to miss. So the Queen of Hearts is literally a queen and a heart indeed, right? Very good. So there is a situation where we can have both. So that means that we don't have a mutually exclusive situation, and we want to keep that in mind when we use this formula. And note that that is the only card that is both a queen and a heart, right? And so we're talking about and here. Okay, so let's go ahead and find these probabilities now. So the only thing that we kind of need to know also is what's our sample space. So in this example, we are literally just pulling one card out of 52. So our sample space is going to be the set of literally all of the possible cards, right? We're just pulling one, so you're going to have 52 elements, and that's all we care about actually when we find the probability. Is we don't actually have to list out the entire sample set. We just want to know the cardinality of it, which is the size, how many elements are there. So literally everything is going to be out of 52. So for the event that the card is a queen, how many successes, how many ways can we be successful about drawing a queen? Well, there are 4 queens in the deck, 1 queen of each suit, right? So queen of spades, queen of diamonds, queen of hearts, and queen of clubs. So 4 queens. And then how about hearts? So again, out of 52 possible cards, we're looking at this as an event. How many ways can I succeed at drawing a heart? Well, there are 13 hearts because we said there are 4 suits, and 52 divided by 4 is 13 cards, so there's 13 different hearts. The 2 of hearts, 3 of hearts, 4, 5, 6, 7, 8, 9, 10. Jack, queen, king, and ace, so that's 13 hearts. Excellent. And then we did say that there is 1 queen of hearts, so we're going to go ahead and subtract 1 out of 52. Take your time if you need to review how fractions work, but here we just go ahead and keep this denominator, and then we go ahead and do 4 plus 13 minus 1, so that's 17 minus 1, which is 16. Very good. Might as well simplify that. So you can divide each of these numbers by 4, and that gives you an equivalent fraction. So 16 divided by 4 is 4, and 52 divided by 4 is 13. So that's our answer, 4 out of 13. Now, while we're on a roll with all this fraction stuff, we might as well estimate this as a percent, because 4 out of 13 doesn't mean a lot to us. So let's review how to convert a fraction to a percent, okay? So I'll take my little calculator here, and we do 4 divided by 13. So it gives me this. You see a 0.3076953, nope, 23, right? But the point is it's 0.3076. We ignore that first 0. And to convert that decimal into a percent, we move the decimal point over 2 spaces. So once would be a 3, twice would be a 30. So 30.77%, which we might as well estimate as a 31%, okay? So our answer is about 31%. So what does that mean? Well, 1/3 is 33.333333%. So a little less than that, but a bit more than 1/4. 1/4 is 25%. So it kind of makes sense because the probability of just a heart alone is 1/4, right? Because it's one of the 4 suits. So 1/4 here, which would be 25%, and then you add the probability of a queen, which is 1 out of 13 or 4 out of 52. Then you subtract this one card, so it makes sense. It's in the right ballpark, right? So I think we are okay here. Our 4 out of 13 is our final answer. So I hope that this was a good start for you if you are learning or reviewing this. If you are asleep by now, I'm wishing you sweet, sweet dreams. Otherwise, take good care, and I'll see you